Yeah. All right, anybody else? All right, so let's go through this problem. What did y'all think? Was this fair? Or?
Yeah.
All right, I think if you did your homework, then you would hopefully agree that that's a fair quiz. So you need to bring your formula sheets to class. I've told you that already. I wasn't kidding. And you need to do your homework. Because if you did your homework, you would have run into something like this, and it works out really nice, actually. All right, so we're going to apply the product rule right here. And then this is a separate term, so we can do the derivative on that separately. Product rule here, derivative of x is 1, so then times tangent hyperbolic inverse of x plus product rule, right? Derivative of tangent hyperbolic inverse. So it's on what page on your reference sheet here? Page 5 has all these derivatives, and it's formula number 33. And it says it is 1 over 1 plus minus x squared. And in this particular problem, because the argument is x, then it's directly the formula. There's no chain rule that has to occur. But then we have to multiply by the x for the product rule. So I'll just tack that on times this x. So that's done with the product rule. Now I move on plus, not times, the derivative of natural log of the square root. So 1 over just the square root of 1 minus x squared, then times the derivative of what's in the natural log. So the derivative of a square root of something is 1 over 2 roots of 1 minus x squared. Then the derivative of what's inside, which is negative 2x. These twos cancel, right? You have tangent hyperbolic inverse. You have plus. This right here becomes x over 1 minus x squared. And then this actually turns out to be really nice, because this root times this root, you square it, the root goes away, you get the 1 minus x squared on the bottom. And on top, what do you have? Negative x. Or you could say minus x over 1 minus x squared. Right? That's what this turns into. And these cancel each other out. And your answer's the hyperbolic tangent inverse function of x. So I'll be looking for partial credit. I mean, I'll be looking to see if you got this, but maybe you didn't simplify it properly, you know? But I need to see work, okay? It can't just be, I know some of you have computer algebra systems, your calculators can take derivatives, and that's not the point. The point of this is to be able to do this mechanically by hand, illustrating that you know how to apply chain rule, product rule to these new functions, right? Okay, so I have a different sort of camera setup today, so I hope it's not too obstructive for you. If it is, let me know, all right? Because I can't stick with it if people can't see. But what's good about this camera, I think, I'm trying it out for the first time, is that I get a wider field of view. So I actually can go from this bar to that bar. It's a little bit wider. It's about 1.5 feet each way. So I'll give a little more space. And I can also, I can move it, like I can rotate it. So I don't need to worry about hiring you, Ron, right? I don't have to hire Ron to move my camera for me. Okay, let's move on. Y'all ready for today's stuff? All right, let's do it. So we're gonna go to chapter 4. So we're gonna jump here now. We're done with the stuff from all the trig stuff, the inverse hyperbolic stuff. It's all done. So let's see how this camera works out. Haven't tried this yet. You're my guinea pig class. So I have no idea what's going to happen here. Can somebody kill the lights over there for me? it's motorized yet. All right. Man, I cannot.
I expect you to edit that out.
No, it's
What's that? Yeah, you're not in
Look
it.
at the thingy right here.
Yeah, that's the viewfinder.
Yeah, I can't make out that on the board. I wonder if it's coming out on my camera up here. It's coming out okay. We'll do that. All right. So let's go through these notes. All right, this is where we kind of start really the Cal 2 idea, the antiderivative. All right, so we talked about this in the beginning. Said first part of this, we've just still been focusing on derivative chain rule and all that. Now we look at something called the antiderivative. So if you have a function, which we're going to call capital F, it is called the antiderivative of another function, little f, on an interval I, if the derivative of capital F is the little f, for all x in some interval I. All right, so what the heck does that mean? It's just a way of relating two functions together. One of them is a function, the other one is the derivative of that function. So what we're used to seeing, right, what we're used to seeing is like someone gives you a function, little f, you take the derivative and we called it f prime, right? Now what we're going to do is we're going to give you a little function, or a function little f, and we're going to say that is the derivative of some other function. It came from something. The thing it came from, that it is the derivative of, is kind of like its parent, okay? And that's its antiderivative, and we call it capital F. If capital F is an antiderivative of little f, then capital F plus c is the most general antiderivative possible. All right, where c is any constant. We call this later the constant of integration. So let's just take an example here. All right, so here's an example. Little f of x is 2x. Does everybody agree that the antiderivative of little f is this capital F of x, which is x squared plus some number? Yes? Because if I take the derivative of this one, x squared plus x squared plus c, everyone here would say the derivative of x squared is 2x, the derivative of a constant is 0, and so you would tell me that the derivative is this right here. So big F is the antiderivative, the most general antiderivative of 2x. Now graphically, the red line here is 2 times x, right? That's 2x. This blue parabola is just one of the antiderivatives of little f. We said it could be this x squared plus any number. So I could change the value of c. Notice I have x squared plus 4 now. And all it's doing is shifting that parabola up and down. Any function there, any of these, would qualify as being an antiderivative of 2x. So we actually have an entire family of functions. There's how many of them? Infinitely many, right? You have an infinite number of antiderivatives of 2x. So just keep that in mind. When we were in Cal 1, we had a function, we took its derivative, the answer was just a single function. Here now, when we start with the function, we try and find an antiderivative, we get an entire family of functions, infinitely many of them. All right? So here's another example. If little f of x is 3x squared plus 10x plus 6, then does everyone agree that this is an antiderivative? So how could you check? Just take the derivative of this real quick. Derivative of x cubed is 3x squared. Derivative of 5x squared is 10x. Derivative of 6x is 6. And then we always throw a c on there because that gives us the family of functions. And again, here's the picture of what's happening. All right? So there, the red one is the parabola. That's little f. Capital F is a cubic function. This is the blue one. And we have all those possible, the family. There they are, right? Now this one I did something even more. I want you to see why this works. Remember that if I start with the function, the derivative is the slope of the tangent line, isn't it? Notice that on every single function in this, this family, the slope of the tangent line at that point, aren't they all parallel? Which means that it doesn't matter which function I pull from that family, the derivative at that point is always the same. And that holds for every point. If I slide this around, you see, anywhere I go on that family, the derivative is always equal, which is why they all share that same derivative. What is it? 3x squared plus 10x plus 6. Does that make sense visually? Okay. Okay, so now what we want to do is we want to look at this table. This is in our book. It's on page 249. I don't know if this is in your notes. Is that in the notes? It's not, right? I think I added that like another semester. I haven't updated the notes. But this is a table that's in your book. Right now, starting right now, everyone needs to be aware of all of these connections between little f's and capital F's. So let's see how many of these we actually know. When we took derivatives, what did we always do with constants that were in front of functions? When we took derivatives, we just carried them along with us, right? Well, same thing with when you're trying to find an antiderivative. If you have a function and you have a constant in front of it, don't worry about the constant. Just find the capital F and just slap the constant to the front, all right? If you have two functions being added together and you want to find their antiderivative, you can find the antiderivative of each one, can't you? That was the same way with derivatives, right? You have two functions, you want to take derivative, you do derivative of each one. So that rule works backwards also, which is nice. Okay, this one we're going to talk about a little bit more here in a second, and this one we're going to talk about in a second. But how about this? E to the x, what's the antiderivative of e to the x? Itself, right? Because derivative e to the x is itself. The antiderivative of cosine x would be positive sine x, because remember, you're working backwards, right? And just think through it. What's the derivative of sine of x? Cosine x. So when you go backwards, cosine to sine, it doesn't change signs. But sine does. The antiderivative of sine x is negative cosine x. And then these, again, from Cal 1, antiderivative of secant squared. Well, what do you take the derivative of to get secant squared? Tangent. So the more you know, the more you actually know from Cal 1, the more of those things that you've got memorized, the easier it's going to be for you to go backwards. All right. I showed you this one. What was it? The first day or second day? First day? I don't recall. But the derivative of inverse tangent was 1 over 1 plus x squared. And I put it over here on the side of the board. I said, remember that one, right? It's going to show up a lot. So just remember that. When you see 1 over 1 plus x squared and you work backwards, the antiderivative would be arctangent. Okay, you can look at the rest. We're going to do these examples. But before we do it, we've got to establish something. So let me move my camera back over to me. It's a little slow, huh? Remember, I'm doing this only because of the internet students, you know, like having to record that. All right. Okay. There we go. That should be it. All right, so let's work through these examples. I'm just going to work them off the board. We have, let's see how far I got here. Somehow my line got off. Where's my hand? There it is. Okay, first example, A. We have, f of x. Let me write it down and then we'll talk about it. We'll talk about how we're going to come up with this general formula. All right. Man. All right, so what do we know about Cal 1 when we took derivatives? If I gave you x to the n in Cal 1 and I said take the derivative, you would say, bring the power down, right, n, and then you would subtract 1 from the power, wouldn't you? So to do an antiderivative, we know that to get back from some power of x to get back, we're going to have to undo that taking away of 1, right? So we're going to need to add 1 to it. So what we're going to try and do is come up with a general formula right now. If little f of x is equal to x to the n, I want us to find capital F of x. And this is going to turn out to be the formula that we're going to put up. Okay, we're going to put this formula up on that sheet. It's on that table. I'll go back to it and I'll just make sure everyone is aware of it. Okay, so we said capital F of x, the power would have to be what? 1 more than that, right? So n plus 1, we'd have to add the power. And then we would always need to add some constant to get the general antiderivative. But is this enough? So let's just check real quick if this works. Let's try it on something. I'll do an example over here. Let's say little f of x was x cubed. Is our formula good? Capital F of x equals x to the 4th plus c. Is that going to work? No, because when you take the derivative of this, first thing that happens is that 4 comes out. And we don't want the 4, do we? So how do we eliminate that 4? We divide by 4, right? We just need to take this, and instead we would need a 1/4 here, wouldn't we? And then when the 4 came out, it would wipe out the 4 and we would have the x cubed, yes? So that's exactly what we're going to do in our formula. Out here in front of this, we're going to scale it or multiply it by 1 over this power, n plus 1. Now, every time we take the derivative, the first thing that happens is the n plus 1 comes out and then it cancels. And then the next thing that happens is we reduce the power by 1, that becomes x to the n. And then derivative of a constant is 0. Does that make sense how that would work? Okay. So that looks like this formula will work, okay? This looks like a formula for us, but there's one problem. There's one issue where this formula falls apart. If what? Not x. If n is -1. What if n is -1? Then wouldn't this formula give you division by 0? So this formula does not seem to work if n is -1. So I need to state that over here somewhere. Somewhere maybe at the end here, or I'll put it down here, for n not equal to -1. So as good as my formula is, it won't work for that one case. But let's look at that one case. What if n is -1? Then what's little f? So if n equals -1, little f of x is actually x to the -1. Okay, x to the -1, which is 1 over x. And that's one that you should remember from Cal 1. The derivative of what gives you that? Natural log. So capital F of x would be equal to natural log, and we put absolute value of x so that we don't have any problems with negative numbers, plus c. So this resolves all of the possibilities when it comes to powers that we could have on x. So if you go back and take a look at that table I had up here, right there, x to the n, what's the antiderivative? They wrote it this way, right? Instead of writing it like this, they wrote it x to the n plus 1 over n plus 1. Isn't that the same exact thing though? Yes? So, and that's what you do if n is not equal to not equal to -1. And then the next formula down, 1 over x, is when n is -1. Make sense? This works for every power of x now. We can do anything. So now let's do part A. Can we get lights, please? Seems kind of dark and, oh, no, on, please. Good try. Try and take a nap. All right, so I know that some of you have seen this before, I know for a fact, but just hang tight. It's going to speed up quick here, okay? You're going to find yourself going from bored to confused very quickly. So don't fall asleep on me. All right, so if we're going to use the power rule, right, this power rule for finding antiderivatives that we just established, then when we look at things, we need to make sure that we have powers of x, which in this case we do, right? Every one of these three terms is a power of x. We just have to kind of make sure we get it written down first. So the first one, 2/3 x to the third, that's a power of x. How can I rewrite this one, Matthew? Hold on, Matthew.
4x to 1.
Matthew? I'm just giving you a hard time, Kiki. To the 1/2? Yes? Okay. And then Kiki, all right, I'll give you an opportunity now.
No, it's too late.
Too late? The window's closed?
Yeah.
Okay. Then who's going to do it for us here? What's the power of x there? That 1/2 is on this, but x to the 3/2. So you have, this is x to the first power. This is really x to the 1/2 power. You add the powers, it's 3/2. X to 3/2. And so now what you have you have three terms. Each one of these is x to a power, x to a power, x to a power, so we can use our rule. Right? What about the numbers in front, like the 2/3 and the 4 and the -1? What do we do with those?
They're constants.
They're constants, so we're going to just bring them with us, right? We're just going to bring them with us. So here we go. Capital F of x will be equal to a bunch of stuff in here plus c. I'm going to just throw the c out here now just so we don't forget it. All right, 2/3 first. And now, Ruben, behind you. Who's that? Vanessa, where's your thing? Okay, so that's why I'm calling on you. If you forget it, I'm going to call on you. Did you have one still? I have extra paper. You know extra paper? All right. What's up? Okay, Vanessa? Okay, Vanessa, can you give me the antiderivative of x cubed, please? Using the formula that we just established. Here you go. Mm-hmm. No? What's going to happen to the power? It's going to go up by 1. Okay? So x to the 4th. And then what do we have to scale by in front of it? 1/4. 1/4. Next one, plus 4. All right. Ron, you look bored. I'm going to ask you for the next one here, Ron. Right here, x to the 1/2. So what's the power on the x? I'll start with the power, if that's okay with you. Is that all right if you just give me the power first? 3/2. So you're adding 1 to 1/2. And then what about the number in front?
2/3. Or, I mean, it's going to be 2, but reduces down to 6.
So you have 1 over, you're doing 1 over this number, right? You were right the first time. Yeah, 1/3/2. This is n plus 1, right? What's 1/2 plus 1? 3/2. So that's the power. And then this is always going to be 1 over that power. So 1 over that. But 1/3/2 is the same as 2/3, which I'll write on the next line. Minus x to the 5/2 is the power. And the number out front is 1/5 5 halves, which will be 2/5. And what you do is eventually you get to the point where you don't do the 1 over 5 halves. You just do mental, flip it in your head, 2/5, and you're good. All right, let's put all this together. I have a 2 reduces here. So I have 1s across the top and 3 times 2. So I have 1/6 x to the 4th. See, what do I have here? 8/3. Flipping and then multiplying. 8/3 x to the 3 halves. And then finally minus 2/5 x to the 5 halves. Plus my constant. And then I box this up. That's my general antiderivative of that function. Now, the good part about these antiderivatives is that you can do what? You can check your work, right? You can actually check your answers. And you would check it by doing what? Taking the derivative, which would be relatively easy to do with this. All right, that's part A. Okay, let's look at part B. How many of you covered the antiderivative power rule in Cal 1? That's it? All right, the next one, little f of x is 2x plus root x minus 4 plus x cubed. Over cube root of x. Now, yeah, I'll put cube root of x. You must be very careful here because we had in that table, we had a rule up there that told us what we could do when we had addition between two functions, right? The top left, f plus g, that said that you could then split it up and just do the antiderivative of each one, right? Is there any rule up there that tells you how you can handle something when you have division?
You can split it up.
Okay, you could split it, I think you mean like put this over this, this over this, this over this, this over this. Yes, and that's what we will do. But what you cannot do is just ignore this and take all these antiderivatives and then just divide by whatever the antiderivative of that is. You cannot do that. All right? It's not allowed. Now, why isn't it allowed? Why don't you think, why is it that if we have little f of x, little g of x, why is the antiderivative not capital F of x over capital G of x? Why do you think that it's not that? Check your, yeah, if you were to check your work, what's the derivative of this? Quotient rule. And the derivative of that would not be this, would it? That's what made Cal 1 difficult, is because when we got to the quotient or products and quotients, we realized that the derivatives weren't as nice as what we wished they would be. So it's the same thing in Cal 2 when you're trying to go backwards. It's easy if it's just term, 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 term. But if it's division or products, therein lies the problem. And we haven't really gotten to that yet, but that's where we're headed. And that's where we'll spend the next couple of weeks trying to figure out ways to go backwards when we have complicated looking expressions. All right, but this one we can still handle with the power rule if we first realize that we have a single term in the denominator, multiple terms in the numerator, and just properties of fractions allows me to just split this up into 4 different fractions. And I'm also going to convert everything over to rational exponents. Rational exponents means fractional exponents. We good? Just wrote everything as a fraction. Now let's rewrite each of these terms as a power of x, because all of these can be simplified, right? Like x over x to the 1/3 can be simplified. That can be simplified. This one can be brought up, can it? As a negative exponent. And then this one also can be simplified. And we subtract the exponents, don't we? Like we do 1, take away 1/3. We do a half, take away a third. Here we just bring it up. And then here we do 3 minus a third. Agreed? All right. So we have not done an antiderivative yet. We're just trying to simplify this. So what is my first one, Chris? Testing. Oh, hold on. This, Chris. Or I'll let you both have an opportunity. What do I do with the 2? Okay, 2. So I'm not doing antiderivative. I just want to know what the powers on x's are. So x to what? Testing your fractional. 2/3. So look, you've got to get good with these fractions. It's got to be quick. All right, and now you might need to scratch paper. That's okay maybe in the beginning, but you really, as a Cal 2 student, you should be able to do the basic arithmetic of fractions like these, maybe mentally, if that's not too much to ask. Who's going to give me the next one? X to the 1/6. Everyone agree? Okay. So just plus x to the 1/6, like that. What's the next one? Minus 4x to the negative 1/3. And finally, plus x to the, what's 3 minus a third? 8/3. That's just what little f is, right? We still have not found capital F. So now we have the pleasure of finding capital F. Capital F would be, and now we do each one of these, the 2 is going to come along. Zach, what do you think about the power on capital F for this one? How are you feeling with the fraction power stuff? Feeling? What? I'm doing the antiderivative, right? So I'm going to use a power rule on this, which means I'm going to add 1 to this power. Are you comfortable adding 1 to 2/3? 5/3? And then what has to come in front of it? 1 over 5/3, but that's really 3 over 5. So 1 over 5/3 flips and becomes 3/5. And that's really what we try and get to a habit of doing. Do y'all understand that? 1 over 5/3 is really 3/5. The 2's just sitting out there waiting to mess with it later. Dustin, did I call on you? I haven't called on you, right, Dustin? All right, so Dustin, how do you feel about x to the 1/6?
6 over 7, x to the 6.
Good. 6 over 7, x to the 7/6. So if you take 1/6 and add 1, you get 7/6. 1 over 7/6 flips and becomes 6/7. Can I get a single person to volunteer for the next one? Anyone want to volunteer?
11/3.
Okay, right here. We're doing this one. So minus 4. What is it? 2/3 or 3/2? What I'm hearing two different things. 2/3? 3/2? Uh-oh. Okay, let me do the power first. What is the power? Take negative 1/3 and add 1. 2/3. Which means the number out front will be that flipped over, so 3/2. And last one. What's 8/3 plus 1? 11/3. And that means out front? 3 over 11. 3 over 11. 3/11 plus C. Now that plus C needs to be written if you're asked to find the general antiderivative. I will count off if you forget it, but I won't count off a lot. Like, you know, if it's a 10-point problem, I'll count off 1 point. But please be aware that there are some instructors that are extremely critical of that plus C, and if you miss it, they'll count the whole problem wrong. It's that important to understand that it is a family of functions. All right, so you could clean this up now, right? Let's just look at what would change on the next line. I'm not going to write it all out. What does this become? 6/5, and then this doesn't change. How about this one?
6x.
Minus 6, and then x whatever, and then that doesn't change. So the next line, everything, the only thing that changes are the things that I circled. Okay? That's it. We're done. Questions? All right, let's look at C. We have, this one's pretty straightforward. F of x equals sine x plus secant x tangent x. So these are not powers of x, right? These involve trig functions, so we better know the antiderivative of these if we have any hope of figuring it out. We do have addition, right? So I can split this up and just look at each one individually. What is the antiderivative of sine x? Negative cosine x? Correct. Then here we have a product, don't we? So you are not allowed to just do each one. But you could kind of, hopefully from Cal 1, remember, secant x tangent x was the derivative of what? Secant x.
Well, negative secant x tangent x. So that would mean that it would be.
No, it keeps the same sign. The derivative of secant x is secant x tangent x. You're thinking cosecant x. Derivative of cosecant x is negative cosecant x cotangent x. So what would this be here, the antiderivative of this? Just secant x plus c, and we're done. That's it. So there wasn't a whole lot of work to do with this one. It's just recognition of things that we've seen from Cal 1. Now D is a little more involved. Now, I'm not going to really expect anyone to know right off the bat how to do this one, but I would like to ask some people what they are thinking. Yes?
Maybe substitute 2 plus 6 squared.
How do you mean? What do you mean?
Maybe not. Well, I was looking at it because I saw the 1 plus x squared on the bottom. I was thinking that might be possible.
Substitute, though?
Oh,
I'm not
wait, no,
quite
don't
sure what you mean.
substitute. Split them and then have the 1 over 1 plus x squared times 2 plus x squared. I mean, not times, plus. No.
So you're thinking split, maybe?
Yeah, split it so it's 1 plus, or not 1 plus.
The only way I could split this right now is to put 2 over the entire thing plus x squared over the entire thing.
Okay.
That's the only way I could split that fraction apart.
Okay.
Because you got to keep the whole denominator. You can't split, I mean, you can't do this and this, right? Okay. Anyone else have an idea of what we could do? Am I allowed to just say, hey, the antiderivative of the top, and then the antiderivative of the bottom? And then I'm not allowed to do that? Someone's going to do that on a quiz or a test. I know somebody in here is going to do it. Every semester, someone does it that way. So you're all agreeing that I can't do it that way, right? Okay. Yes?
We split it and then we take the denominator to the numerator with the power of -1?
You could do that also. So you're saying split it and then do that?
Yes.
You could. What's being suggested is we do, here's the splitting if we did it, right? And then you could bring the entire denominator up and it would look like this. And then this one would be x squared to 1 plus x squared to the -1. I think that's what you meant, right? This is correct. This is the same expression, isn't it? But how do you handle taking the antiderivative of this? So you cannot take the antiderivative of each one of these individually, because again, it's trapped inside of this -1. These have to be completely freed up in just a power of x, power of x, power of x, not inside of something for you to do the rule. So we're very limited here, right? Yes?
Can you split the 1 over 1 plus x squared and take the natural log of 1 over 1 plus x squared?
You mean look at it as being the derivative of the natural?
And then
Could you take 2 plus x squared and times it by 1 over x plus 1 squared, and that would give you tangent?
Take this and
Times it by 1 over that. And then
multiply this by 1 over this. Like rewrite it to look like this. Okay, so that would be the same expression, wouldn't it? Yeah? Does everyone agree with that? And I would probably need to put parentheses around this because that's that whole thing, right? So this isn't a bad idea, but we're still going to run into a problem because look, could you find the antiderivative of this? Yes? That's just the power rule in each one, right? Could you find the antiderivative of this? It's arctangent. Here's the problem. You can't go backwards from here. You cannot go to the antiderivative. If you have a product, you cannot do each one separately. Just like when we had a quotient, you can't do each one separately. And it's because the product rule doesn't work that way either. So I thought I silenced this phone. Our hands are really tied when it comes to finding antiderivatives. Right now, we have to have pluses and minuses between things, and each one of them has to look really, really nice. That's our limitation right now. See, this is the inherent problem in this class, is that in Cal 1, product rule was complicated, and quotient rule was complicated. So now we're trying to reverse the process. So anytime we see a product or a quotient, it's going to be extremely difficult. Understand? So life would be great, and Calculus 2 would not be as hard as they say it is, if you could just say, all right, take the antiderivative of that, antiderivative of that, done, let's go. Right? So for this, it's pretty easy. Right? Do power rule and you get it back. I'm not going to do it. But what we'd be looking for is for it to become this, right? Okay, so let's compare that to part B. For part B, that's a problem I like to put on a test. Only because if you mess up B, then there's some like major foundational problems. Like we need to sit down, talk. And so it's kind of a red flag problem for me. 2x plus root x minus 4 plus x cubed all over cube root of x. Now that looks pretty bad. Here's what I don't want you to do, all right? This is the mistake, is that people will look at this and go, okay, these are separated by addition and subtraction. I can do this one by itself, this one by itself, this one by itself, this one by itself. That's okay. And then you come down here and say, oh, that's just a power of x. I do that by itself. So my answer is just the antiderivative of this, 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 this up here, and then divided by the antiderivative of this on the bottom, and then I'm done. That's not correct. What you're doing there by doing that is you're actually undoing a quotient by assuming that the antiderivative of a quotient is just the antiderivative of top and bottom separately. And you're not allowed to. So your only hope here is to try and get this to not be a fraction anymore. And can you do that?
Yes.
Yes. Because you have a single denominator, right? You can separate it into 4 different fractions. Right? This is the same as 2x over cube root of x plus root x over cube root of x minus 4 over cube root of x plus x cubed over cube root of x, right? That you're allowed to do. Right, Kyle? Yeah? Okay. And then, what can you do?
Bring the power down.
You can start doing power rule, yes, as soon as we get a single power of x though, right? Like this has to be put together to become x to a power. So let's just talk about that. This is college algebra. X to the first power over x to what power? 1/3, right? Cube root is 1/3. And when you have this, you subtract. 1 minus 1/3 is 2/3. Right? Nope. It's 1. Yeah, this is going to be 3 over 3 over 1. Okay, everyone good? Yeah? Okay. Everyone okay with that?
And then 2 would just come along, right?
Yeah, the 2 will come out. So let me rewrite it. I haven't done any antiderivative yet. This is just rewriting the problem, right? That's just rewritten, right? How about this one right here? I have to come over here on the side. I have to do some college algebra again. That's, I'll do it over here. This is x to the 1/2 over x to the 1/3. This is x to the 1/2 minus 1/3. 1/6. 1/6. Common denominator, put it together. So plus x to the 1/6. So minus 4, that's what's here, right? Minus 4. This is x to the 1/3 in the denominator. I bring it up, x to the negative 1/3. Do not forget to bring that up. So I'm looking at this right here. It was 4 over x to the 1/3. I cannot use power rule on this because the 1/3 is in the denominator, or the x to the 1/3 is in the denominator. I have to bring it up to become x to the negative 1/3. Do y'all see that?
Yes.
Okay. I still haven't done any calculus. Do y'all agree? Nothing I've done yet is calculus. Everything I've done is algebra up to this point. And the last one, what am I going to be doing? I'm going to do x to the 3rd, right, over x to the 1/3. And that's 8/3. So Alex, you keep on giving me these answers. I'm just going to ask you, how are you doing 3 minus 1/3 so quickly?
Just find the common denominator.
So mentally,
Yeah.
you're doing 3 over 1 minus 1 over 3, like in your head, kind of?
Kind of, sort of, but I just at the top of my head recognize that if you put it as, yeah, if it's 3 over 1, yeah, if you do it that way, you do it, but I don't do that one with my head. I just assume that it's 9.
So you just kind of are automatically seeing that 3 is 9/3.
Right.
And then once you're there, subtraction is just the numerators. Okay. So that's stuff, I mean, it's just everyone's at different places when it comes to like adding and subtracting fractions. You actually want to be right there. Where you are, Alex, is perfect. That's where you want to be. It's going to take time to develop that. You have to work with enough of these to get quick with it. But at the end of it, you just have to have your own way of doing it, all right? You don't want to be breaking out your calculator to do 3 minus 1/3, okay? That has to, you can't have an approximate answer. It has to be a fraction. So what is this? Plus x to the 8/3. Okay. Now we do antiderivative. So look at these ends, right? These are some weird ends. 2/3 is one of the ends. 1/6, negative 1/3, 8/3. You do this, okay? I want to give you a few minutes to see if you can come up with these on your own, all right? And write down. And what I'll do is I'll call some names, some people I've never met before. I'm going to call on you. I'll call on 1, 2, 3, 4, potentially 5 people. passing the sign-in sheet around. If anyone has a question about something, you can raise your hand. I don't mind coming by and helping out. The top one first, like.
The exponent first, and then flip it. So you can take those.
You mean like add one to this?
Yeah, and then
Just figure out what that is and then flip it and put it in front? Yes. You can do that.
So 2/3 was 3 over 3.
It's gonna be a good first one, right?
5/3. And then 2%. But you know you got? That's why they thought you can't.
Just add it.
Yeah,
Are we ready? Y'all ready? Okay, I'll give somebody an opportunity to volunteer, but it's got to be someone I haven't really interacted with. So, let's see. Anyone want to volunteer? Kristen? I don't know much about Kristen. Kirsten, sorry. Kirsten. Do you have the first one?
Yeah.
Okay, what do you got?
6/5 x to the 5 thirds.
6/5 x to the 5 thirds. Agree? Yes? So you had out here, what? So this was 5 thirds, and this became 3/5 out there. That's correct. Who else? Is it Michael? Michael? Did you get the second one yet, Michael? 6/7
X to the 7.
Is that right?
Yes.
Yes? Okay, good. And then no one's volunteering for this one? Go ahead. You can go, James. 6x to the 2 thirds is what you got for this one? So this was 2 thirds out here, and this was 3 halves out front, like that? So no one's disagreeing? I guess we all agree it's correct? Okay.
As long as you keep the minus, just.
Yeah, there's a minus here, right. Okay, so minus, this was plus 6/7 x to the 7/6. And, okay, so everything else looks good there? And then the last one, 3/11 x to the 11 thirds, then plus c? Okay, so we're all good? We all agree? Okay. Looks good then, I guess. I'll trust you.
Checking your answer with that would not be kind of a pain.
I don't know, let's just check the first one, okay? If you were to do this to this, right, you multiply 5/3,
30 over 15, which is
6 times 5/3, right? 30 over 15, that's 2, right? So that's this. And then you subtract 1 from this, so you subtract 3/3, and you get 2/3. So yeah, it works. So tedious, not too bad. Okay, let's look at the next example, C. What example C is checking is that you remember those common antiderivatives that you should know from Cal 1. So these are not power rule, right? This is not x to a power. This is, trig functions. What's the antiderivative of sine? Antiderivative of sine. Negative cosine. And so that's the one you got to be careful with, right? And you can always check yourself, right? What's the derivative of cosine x? Negative sine x. That's why you have to have a negative in front to make it a positive. And then the antiderivative of secant x tangent x. Just secant x. So derivative of secant x is secant x tangent x, so plus c. So those are ones that need to come from recognition, all right? And let's look at D. 2 plus x squared over 1 plus x squared. What do you think? Can you just do top and bottom separately? No. So your only hope that so far from what we've learned is that you can either break this up into powers of x with pluses and minuses between them, or it's something that you recognize from the table, from derivatives from Cal 1. Can you split it like we did the previous problem?
Yes.
The one where we did the different ones and then write each one as a power? Couldn't you? Can you?
Yes. Like 2 over 1 plus x squared over 1 plus x squared?
right.
How can you split that? You got to be careful the way you split this.
2
Oh, yeah.
plus 2 right, x squared. That's the denominator, then plus x squared.
Plus x squared.
This you can do. That you are allowed to do.
Isn't that sine of that? So, oh, you had the limit. Never mind.
That you could do. Do y'all agree I could do that algebraically? But does that help? Not really. All right? Not really.
So would we break up the first, the first part into 1 over 1 plus x squared plus 1.
I think I know what you're saying, and that's super clever.
So that would be 2 inverse tangent.
Yeah, okay, so watch this. Now, I don't know. I don't know if this is what you're saying, but I think this is what you're saying. In the very beginning of the problem, could you do this? I think we're going to get to the same place. Could I have done that? 2 is 1 plus 1? Am I allowed to split this right here? Like do 1 over this and then this over this? Yeah? So that would become 1 over x plus, 1 plus x squared. That's 1 over this. And then what's this over this? So plus 1?
So it would be tangent inverse x plus 1.
That's right. Well, plus something. So we've just done some algebra here, right? To split this up? Yes? Ooh, that's kind of strange, isn't it? How'd you see that, James?
I just looked at the
Okay. Yeah. So you just recognize it. Okay, so again, there's no way I teach that. I can show it to you, right? But I can't teach you to see that. And that becomes a theme in this class. Seeing things, recognizing patterns. Now this is kind of unorthodox, but it works, doesn't it? Now let me show you another way you could have gotten to this, all right? If you didn't see that, you could have done this. Remember that? College algebra, long division. Right? So how do you do this? It's that divided by this, right? So what do you multiply x squared by to get x squared? 1. Then you do multiplication here, here. You come through and subtract, so it changes the signs, right? And when you add down now, you get nothing, and here you get what? 1. X squared doesn't go into 1, right? So you get plus your remainder over your divisor, the remainder over this. That's this, right? So you could have got to the same result with just long division. Now, we have not done the antiderivative, have we? Just rewritten the problem. And now for the antiderivative, you have to be able to recognize these. And this is the antiderivative, I'm sorry, this is the derivative of what function? The derivative of arctangent. So do you remember when we studied arctangent just a couple of first class? I told you that the derivative of the inverse tangent of x was 1 over 1 plus x squared, didn't I? And I told you to put a star next to it because we're going to use it a lot. Do you remember that from the first class? Well, that's why. Look, what's the antiderivative of this? Arctangent of x. We recognize that. Okay? And then what is the antiderivative of 1? Now be careful with this. X. X. Now we hadn't done this yet, had we? I hadn't done that before. The antiderivative of 1 is x because the derivative of x is 1, right? What do I still need? Plus c. Does anyone have a question about this? Because we're done with this problem. Yes?
How did you get the 1 over 1 plus x squared plus 1 there?
From
Splitting up the 2 and
okay.
plus 1.
So I split this into 2 fractions. I do this piece over this.
1 over 1 plus x squared.
That's this. And then I do, I could have done individually, but I decided to clump these together and put that over this. And that gave me the 1. All right. Still have about 10 minutes. All right, so we're going to talk about rectilinear motion. Rectilinear motion. Objects that are moving in a straight line, basically, is what we're talking about. And in Cal 1, I hope that you were shown that if you have an object moving in a straight line, okay, so some object moving in a straight line, usually we'll look at this as like two-dimensional or one-dimensional where it's just like a car going down a track or something like that. Then if you have a way of measuring time and position of the object, right, that the first derivative represented the velocity and the second derivative represented the acceleration. Well, if we're now talking antiderivatives, there must be some way that we can go from an acceleration backwards to a velocity and from a velocity backwards to a position. And that's what this is about. So look, it says, recall that if the position of an object moving in a straight line is given by some function s of t, so this is the function s of t, that the velocity, right, v of t, the velocity of this object is the first derivative, and the acceleration is the second derivative. Therefore, if somebody gives us an acceleration function, right, if somebody gives this to us, and I want to know what velocity is, will I be able to get it?
Yes.
Yes, but there will be kind of a sacrifice I make. When I find the antiderivative to go backwards, am I going to be able to get the exact function? I'm only going to be able to get a family of functions, right? Understand? And that's not exactly perfect, the exact function we're looking for. But it gives you some idea of what it should look like, right? It's within a family. And then if I have some idea of this function, I should be able to go back and get this one, right? The position. I would have to do the antiderivative velocity. And again, I will have there's a give and a take. I'll be able to get it, but it'll be a family that I'll be looking at. Yes? All right, so here's an example. We have an acceleration function that's given to us. Acceleration of an object is 24t minus 6. And you're given some other information. S of 1 equals 7, and V of 2 equals 41. Find the position function, and then find S of 2. So I'll draw a quick picture of what's happening here. I'm going to draw it backwards. Here's the acceleration function. Do we have this function? Yes? It's 24t minus 6, right? It looks like this. If I were to graph it, it has a y-intercept of negative 6, has a slope of 24. It's like this. This is our it's a line, isn't it? It's a line? Okay. And I think any t values, no negative t values, because it's probably time, right? So it's just this light right here. Okay. Now, I'm going to try and go backwards from that to get the velocity function. And we know that when we go backwards to get this, it's going to be a whole family of functions, right? And they're actually going to be a bunch of parabolas, aren't they? Because this is a linear function. Antiderivative should take us back to parabolas. So it's all these parabolas in here, right? But they gave us something else. They told us the velocity at 2 is 41. What does that do for us? At 2, I'm at 41. That point must be on my graph, right? That's actually going to fix, instead of having a whole family of parabolas, that nails down the one parabola it can be. That's all I need. Just one point on that curve, and I can tell you exactly which of those parabolas it is. So that's an important piece of information to know. This right here, these things, in problems like these, are known as initial conditions. Now, it's bad wording in this problem because initial usually makes you think starting, like the initial. It's most of the time it's like S of 0, V of 0. It's the start at the very beginning, at time equals 0, it's the condition you have. In this case, it's not really an initial condition that we have. I'm telling you that at 2 seconds, the velocity is 41, and at 1 second, its position, right, S is position, the position is 7. Do you see why initial isn't really a good word for this? All right. And then going backwards from here, see, once I nail down that specific parabola, I can go back to the position function, which is going to be a cubic function, isn't it? If this one's a parabola, this one should be a third-degree polynomial. And there's a family of them. But again, I've got some information. At 1, I'm at 7. And that's going to nail down the exact position function. Once I have the exact position function, then I can answer parts A and B. All right, so let's see how to do this. I have 5 minutes. Hopefully we'll have enough time. Here we go. The velocity function should be the antiderivative of this. What is the antiderivative of 24t minus 6? So 24 times 1/2 t squared. Right, and then minus 6t.
Yes.
Be careful with these constants, right? In Cal 1, we were like derivative constant 0, derivative constant 0. But in Cal 2, the antiderivative of a constant, the variable just appears, doesn't it? That's what happens. And then plus c. So the velocity at time t is 12 t squared minus 6t plus c. Yes? Now I'm going to use the condition, okay? The condition, I'm going to say here, but v of 2 was 41, right? That implies that when I plug 2 into this for t, it should spit out 41. So when I plug in 2 for t, I should get 41 out, right? So this is, so what's this? 48 minus 12, right, which is 36, plus c equals 41. So c is 5. So c is 5. So look at our train of thought here is this. We know the acceleration. We go backwards to get the velocity. I know the velocity. I know it's a family of curves. I don't know which one it is. I use the condition that allows me to figure out what that c is. And now I know exactly what that function is. The velocity function is exactly 12t squared minus 6t plus 5. Yeah? Okay. Same principle. We're going to go back and we're going to get position now. So we have to take the antiderivative again. So for the position, s of t, we find the antiderivative of this, which will be 4t cubed minus 3t squared plus 5t plus c. Now it's okay to use c again if you want, because we already found what that c was, right? But just so there's no confusion, I'm going to use capital D instead. But what do we know about this? But s of 1 is 7, which implies that when I plug 1 into this, I should get 7 out. So 4 and then 1 cubed minus 3 times 1 squared plus 5 times 1 plus d equals 7. What is it? D is what? 1? Yeah? I'm not doing the math in my head, so I'm trusting you. Yes?
Yes.
D is 1. Okay, so that means D is 1?
Yeah.
And that is your position function. That answers part A, doesn't it? That's part A of the problem. What is the position function? And then, the last thing, S of 2. So just plug 2 into that and you get an answer. So you can't find S of 2 if you don't know what S is, right? Okay, I have 30 seconds. I probably don't have 30 seconds, but I want to show you something real fast. Does anybody know on Earth what the acceleration of gravity is? Negative 9.8 meters per second squared. Does anyone know what that is in approximately feet per second? About 32. 32 point. You've heard this before, something like this, negative 32 feet per second squared, depending on what units you want to be in. Okay. Yeah, well, let's assume Earth, and let's assume that we're averaging out, of course it's different if you're further away, right? So let's just assume that. So on Earth, all objects, if you just let them go, have an acceleration of negative 32 feet per second, right? If you go backwards and find the velocity, the antiderivative of that would be negative 32t, right? Plus some constant that I don't know. But I want you to pay attention to something. At v equals 0, what would I get? If I plug in 0 into this, what would I get? C, right? Wouldn't that be the velocity at the beginning? Right? At time 0, isn't c the velocity at the beginning? Yes? So let's somehow let you know that that c will always be the velocity at the beginning. What I'll do is I'll write this instead. Instead of calling it c, call it v sub 0, initial velocity. So I know the acceleration on Earth. I know what the velocity of the object would be, but you would have to tell me what the initial velocity of the object was. Now, let's go backwards again. What's s of t? What's the antiderivative of this? Negative 16t squared. What's the antiderivative of a constant? So what's the antiderivative of 4? 4t. So what's the antiderivative of v naught? V naught t. But then I have to say plus another constant, right? Let's call it d. Now I want you to notice something about d. If I let s of 0, right, that would be at time 0, it would kill these two off, and I would just have this, which would be the initial position, wouldn't it? The starting height of the object. So I'm going to, instead of calling it d, I'm going to call it s sub 0. Have any of you ever seen that formula before? Physics? But, yeah? Yeah, okay, so I don't know, maybe in high school or something. This is in college algebra. I use this as an example. This is any object on Earth. If you let it go, its position is given by this formula. The only two things you need are its starting velocity. So whether or not, if you just drop it, the velocity is 0. If you throw it up, the velocity is positive. If you throw it down, the velocity is negative. So if you just let it go, that's 0. And then this is just how high off the ground it is. This formula did not fall out of the sky. It actually comes from the fact that we just were able to measure the acceleration. Once we knew acceleration, we just went backwards. Pretty amazing. Anyway, have a good day. Do your homework, which is what? Right there. 1 through 33 odd, 39 and 41 on page 252. Keep up with your homework. Things are going to start getting real interesting soon. If they're, yeah, you can throw those away or just put them on my desk. Thank you. Anybody else?
Good time.
Down there? Thank you. Anyone else? So how did that quiz go?
All right.
Was it all right? Well, so if you ran into any difficulty, you know, you should give me a call or text me or, you know, reach out for help. Don't just come to class and be like, oh, I couldn't figure it out. Sign-in sheet's going to come around. Here, I'll start it with you, man. So I'm ready to roll. Is everyone ready? Okay. All right, we're going to start out today. We're kind of going to jump around a little bit in the book, but it's just because I think the way that the book presents it is a little different than the way that I want to present it. So we're going to cover 4.7, 5.2, and part of 5.3 today, but I'll be all over the place. So I'll start here with 4.7. That's what we're going to pick up, all right? So I'm going to try these markers, and let me know if you can see. All right, we'll see how that works. Can everyone see that? All right. All right, so we have in 4.7 the idea of antiderivatives. And we already saw from last class that, what was it that we were talking about last class? Riemann sums, right? The curves, and you're trying to find the area underneath, and we added up all those rectangles, right? That's going to be connected to the antiderivative. So before I make the final connection of those two, I want to make sure we understand what antiderivative is. So the first thing is definition. F, capital F, is called an antiderivative of little f on some interval I. So when the book says on I, they're talking about an interval, like part of the number line, somewhere, between, let's say, 0 to 2 or something like that. So it's called an antiderivative of little f on interval I if the derivative of capital F of x is equal to little f of x. And that needs to be true for every x in that interval for us to be able to call it an antiderivative. So the definition here is antiderivative. And the way that we write for all in mathematics is for all x. It's an upside down A that represents for all x element of I. So that means for all x value, for all x's that you ever pick inside the interval, as long as the derivative is equal to little f, then it's called the antiderivative. So for all x in I. So this is where we're kind of connected to Cal 1. Okay, we took derivatives already in Cal 1, so we already know what derivatives are. It's just now we need to somehow come up with this idea of an antiderivative. So for antiderivative, I'm going to give you an example. And we did a couple of these in class, right, already? Let's say we have little f of x is equal to 2x. What is an antiderivative of that? What is it? X squared, right? So you're really asking yourself, derivative of what gives you this? X squared. Is that the only answer? I'm not there yet. But yes, I'm getting to that. What's another antiderivative? What's another one that would work? How about x squared plus 3? That would work also, right? Because we know derivatives of constants are 0. And then we have what? We could keep going, couldn't we? I could go all day with this, couldn't I? Just keep on coming up with just numbers. E is a number, right? So that's a constant. Derivative of E is 0. Derivative of E to the x is E to the x. That's different, right? Okay. So what we get from this is that each of these is an antiderivative. But the most general antiderivative that we could ever come up with would be x squared plus any constant. So that C represents a constant. All right? Let's do another example. How about if little f of x is equal to, how about x to the 7th? Yeah, so we have to know, kind of the way the derivative works. Whatever we pick for our capital F, we know that the power on it must be what? Because when you take derivative, power comes down by 1. So we know the power has to be 8, right? So that when you take derivative, that power come down by 1. So we know that's got to be true. But the problem with this is if I take derivative of this, the 8 comes out, right? And I don't want that 8 to be here because there's a 1 in front. So what I need to stick in front of this is a 1/8. And that way when that 8 comes out, it cancels out. 1/8 of 8 is 1. And then again, for the same reason here, we can actually throw any constant onto the end of that, couldn't we? So that would be the most general form of the antiderivative of x to the 7th. So that brings us to trying to come up with a formula for the antiderivative of x to the n. Okay, so some of you already know it. I'm going to think through it though real quick. We know the power has to be 1 more, right? Because the power here is going to come down. So whatever this power is, I need to be 1 more than that, don't I? So that when I subtract 1 from this, I get n. And then also, when the power comes out in front, I need it to turn into a 1, don't I? So if I divide by n plus 1, then when that n plus 1 comes out, it cancels out, you get a 1, that gives you the 1 here, the power comes down, you got it. And then lastly, plus c, plus your constant. All right, so this right here is something that you should know. This should be hardwired. And this is called the power rule for antiderivatives. Don't confuse that with the power rule for derivatives. Power rule for derivatives is power comes out front, subtract 1. This is the antiderivative, which means that if you start with n, when you go to the anti, you add 1, and then you divide by 1 over n plus 1 up in front. Now, I also have to point one more thing out here. This is only when n is not equal to negative 1. Because what if n is negative 1? What if n is negative 1? Right here, what do you get?
0.
0, division by 0, don't you? So this property does not work when n is negative 1. So what would we do if n was negative 1? What would we do? Let's see. Let's take the example where n is negative 1. If I take little f of x to be x to the negative 1, right? If I take that example right there, what's the antiderivative of this? So it might help if you rewrite this as 1 over x, right? Because x to the negative 1 is 1 over x. And that's something you should have learned in Cal 1, right? Derivative of what gives you 1 over x? Natural log. So the natural log of x plus a constant. Now the book, you're going to see a lot in the formula in the book, they're going to have absolute value of x. And this just, the reason why this is true is because, or the reason we put the absolute value is because with this function f, we can plug in negative numbers up here, can't we? What's 1 divided by negative 2? Something, right? But for natural log functions, the domain restriction for natural logs is that you can't plug negatives into natural logs, right? So by putting an absolute value, we kind of eliminate that problem of having a negative in a log. So now if I plug negative 2 in, I would do absolute value, right? And that would be okay. So the book goes into an explanation a little bit better on why you could do this, but I'm just going to put it up here. All right, so we have the general power rule here, right? The power rule, and now this is the case where n is negative 1. This is what we would have. So theoretically, we should be able to look at all sorts of examples now that involve powers. So how about this one? Let's let little f of x be equal to, where's the one I want to do? I forgot which ones. Okay, I'm doing this one. How about 3 square root x minus 2 fifth root x cubed? So what I'm trying to find here, what we're trying to figure out is what the antiderivative is, right? What's capital F?
So is that 2 times?
That's 2 times the fifth root of, yes. All right, so what I'm going to do here is first realize that the only rule I have up to this point is that power rule. And the power rule requires that I have my variable raised to powers. So I want to convert all my radical notations into rational exponents. So that's the first thing I'm going to do. Take my little f, and I'm going to rewrite it as 3x to what power? 1/2 minus 2x to the 3/5. So if you need to go back and look at how to convert radicals over, there's a formula for this. But it's just whatever's in here is the numerator, whatever's out here is denominator. All right, now we have to look at this and try and use our power rule. Well, the way you do this is that, just like you did with derivatives, remember with derivatives, when you were trying to take derivative, if there was a constant in front, you just kind of ignored the constant and you did the derivative of whatever was here and then just multiplied through. Same thing with the -2 derivative. Antiderivatives, same way. So what I'm going to do is I'm just going to cover up the 3, and I'm going to look at just this piece and look at that as an x to the n. So what's the antiderivative of x to the 1/2, according to the formula? So my capital F is going to be, I'm going to leave a space for my 3, or you know what, I'll just put it down right now. There's my 3. So what's n here? N is 1/2, right? Go to the formula here. X to the n. N is 1/2. So I'm going to put 1 over 1/2 plus 1 x to the, yes, 1/2 plus 1. I'm just writing a little detail here. Do you all see that? That's just the antiderivative of this. Questions? Come on. Now, just like derivatives, remember when you took derivatives, you could take the derivative, like if you had a sum or a product, you just did derivative of each one. Same thing with antiderivatives. If I have subtraction between two things, two terms, I can do antiderivatives of each one separately. So I'm going to now bring in a -2 and then work on this one. So what's n for this one? 3/5. So I'm going to have 1 over 3/5 plus 1 x to the 3/5 plus 1. I think I'm off camera there. Yeah, I am. Any questions, though, on this part?
Just basically plugging into the...
Yeah, into the formula. Yep. Now, but the thing is, after you do all your homework, you should get to a point where you're doing most of these computations mentally. But I'm just showing the detail of it right now, all right? So let's see where we are. Oh, plus c. Don't forget plus c, right? All antiderivatives will have a plus c. Okay, so that's equal to 3 times, okay, we said 1/2 plus 1 is 3/2, right? 1 over 3/2 is the reciprocal, 2/3? So 2/3, is that all right? Okay. X to the what? 3/2. Minus 2, and then 3/5 plus 1 is 8/5. 1 over 8/5 is 5/8. So yes, you will have to become proficient with fractions here. There's no avoiding it in this class. You've got to get good with them. 3/5 plus 1 there is 8/5, so 8 over 5. And then plus c. And we're almost done. We just need to take those constants in the front and put them together, multiply them out. This is nice. This cancels out, doesn't it? So we get 2x to the 3/2 minus, what does this turn into here? What's 2 times 5/8? 5/4. So you can reduce that fraction. And then x to the 8/5 plus c. And what's the good news about antiderivatives? I mean, what do you think the good news is? You can check your answer, right? You can check your answer. You should, if you take the derivative of that, you should get what you started with. So I'm not going to, but that's what you could do. All right. How about this? How about another example? Little f of x equals 3t squared minus, change this to a f of t, not f of x. 3t squared minus square root of t minus 4 plus t all over cube root of t. So this is going to work out using that power rule, just like we used. But the problem is we have a fraction, right? We have a rational expression. So in order to do this, the only thing we have up to this point, the only way we know how to take antiderivatives is if I can get it to look like a power. So just like with derivatives, remember when you had quotient with a derivative, you didn't just do derivative top and bottom? When you have a quotient for antiderivative, you don't just do antiderivative top and bottom. So my only hope is to try and get this and split it up into pieces. So since I have a single term in the denominator, I can write this over this, this over this, this over this, this over this, right? This is a very special case though. If I had another term down here, I couldn't do that, could I? So because I have a single term, I can rewrite it though. So let me rewrite it. F of t equals, let's see, 3t squared over t to the 1/3. So what I'm doing is I'm rewriting the cube root as t to the 1/3, right? Minus t to the 1/2 over t to the 1/3 minus 4 over t to the 1/3 plus t over t to the 1/3. So I've split this thing up into 4 separate terms. I'm going to erase this. It's in my way. That's okay? And then I haven't done any antiderivative yet, right? Nothing. I'm just trying to clean it up. What is t squared over t to the 1/3? So powers, what do you do with those powers? Subtract. What's 2 take away 1/3? 5/3. 5/3. So 3t to the 5/3 minus, what's 1/2 take away 1/3? What's 1/2 take away 1/3? You have to get a common denominator, don't you? What is it? 1/6. 1/6. So maybe you need to do scratch work on the side and get this, but obviously, wouldn't you agree in a Cal 2 class I should expect that you can do this, right? Okay, maybe you need a minute, but that's the expectation. All right, what about this one though?
4t to the negative.
Yeah, just bring the t to the 1/3 up. So remember, anytime you bring something up, it changes it to a negative exponent. So I have negative 4t to the negative 1/3. And then finally, this is t to the first power over t to the 1/3. So 1 take away 1/3 is t to the 2/3. Okay, now we get to go and play our game with this. Each one of these terms has t to an n. T to an n, t to an n, t to some n, right? You got that? So now I have to plug it into each one of those into the formula, keeping the constants, the 3, the -1, the -4, and then a 1 out in front of all of these. So here we go. So our capital F of x, our antiderivative, will be, pardon me? F of t, thank you. I'll keep on doing that. Capital F of t will be, let me put my 3 down, times 1 over 5/3 plus 1, t to the 5/3 plus 1, right? So that would be this first one. Minus what? Minus 1 over 1/6 plus 1 t to the 1/6 plus 1. Yeah, I'm going to continue the next one on the line below because I'm going to go off camera. Actually, I'm not even on camera right now. There we go. So the next one right here would be minus 4, 1 over, be careful on this one, what is it? Negative 1/3 plus 1, right? So if it's a negative exponent, right? If your n is negative, then you have to plug a negative in there. t to the negative 1/3 plus 1. Last one. Plus 1 over 2/3 plus 1, t to the 2/3 plus 1. And then you have to figure all that out. Okay? So I'll do this pretty quick here. Oh, plus c, plus c. I'll get that on my final answer. F of t, capital F of t equals. So I'm going to do this pretty quick here, all right? 5/3 plus 1 is 8/3. 1 over 8/3 is 3/8. But then multiplied times 3 is going to be 9/8. So 9/8 t to the 8/3. The next one, minus 1/6 plus 1 is 7/6. Reciprocal, 6/7. 6/7 t to the 7/6. Next one, so I've done these two, right? Next one is -4, well, let me do this one first. What's negative 1/3 plus 1 is 2/3. Flip it over 3 halves, -6. T to the 2/3. And that's this one. Our last one here, let's see, plus 2/3 plus 1, 5/3, flip it over 3/5. T to the 5/3 plus c.
Wait, it's 3 halves.
Hold on. Oh. 3, this one, 3 over 3, 5/3. Yeah, 5/3. Are we okay with that?
I got a question.
Yes.
Anytime there's not a constant in front of the variable,
It's a 1.
just a reciprocal of the fraction.
It's just a reciprocal of the fraction. That's right. Yep. Okay, now here's something I just want to point out real quick. For those, I mean, most of you have to do more math. A little subtlety. I don't know how you write your t's, but it took me a while to start curving my t's. I don't know if you do that or not, but a bunch of t's and pluses and stuff. If you confuse your t's and plus signs, you might want to start curving your t's. You might want to start striking your z's. Like if you're going to do a lot of math in the rest of your life, these are the little things that you should maybe start doing. Okay, let's see. That's it. That's it for the power rule. You get to go get your hands dirty in the homework and make sure that you can work through all that. And on page, come on, man, come here. There you go. Where's the, what page is it? On page 249 of the book, if you look at table 2, it gives you a bunch of common functions and their antiderivatives. And I'm not going to go through them here right now, but you should look at that table because in the homework they expect that you saw that and looked at it. I'll give you an example of just one of them. If little f of x equals 1 over 1 plus x squared, the antiderivative of this is inverse tangent of x plus a constant. And that's a very, very common antiderivative that you will have to know probably by heart. You'll just know that one. Eventually, you will. But that table has some of the basic ones just to get you started, all right? And look at this right here real quick. That can't be broken down as powers of x, right? Like you can't split that into 2 fractions because there's 2 terms on the bottom, 1 on the top. So the only way to hope for an antiderivative is if there was a formula at this point, which there is. And then, you know, they go on and talk about some others. These are ones you should know. Like, you should know what the antiderivative of cosine x is, right? Sine x plus c. So you can look at that table. Any questions on just basic antiderivatives? No? All right, now, going back to Cal 1, I'm still in the same section as antiderivatives, but going back to Cal 1, hopefully you were taught in Cal 1 that when we talk about linear motion, that means an object traveling in a straight line, that if S of t gives you the position of an object versus time. This is also known as a distance function. It gives you where the object is at a point in time. So if that's a position function, then the derivative of the position function was equal to the what? Velocity function. So that gave you velocity versus time. And if you go further and you take the second derivative of the position function, which is the first derivative of the velocity function, then you get the acceleration function. So that gives you acceleration of the object versus time. How many of you know that from Cal 1? Okay. So start with the position function. First derivative gives you velocity function. Second derivative gives you acceleration. In this class, since we're talking about antiderivatives, we actually now want to see what it's like to work backwards from this. So in this class, in Cal 2, same thing with linear motion. If A of t equals if A of t is the acceleration versus time, then if we go backwards and take the antiderivative of this, right? Antiderivative, which I haven't given us a notation for, right? Like this little prime mark was derivative, second derivative. I haven't given us a notation yet for antiderivative. I will today, but just not yet. So if I take the antiderivative of this should give us what then? The velocity function, right? And then if I go backwards again and take another antiderivative, I should be able to recover the position function. It's just going this backwards, right? So going from here, anti gets you up here, anti again gets you up here. But we run into a problem with it. And what's the problem that we run into? Every time we take an antiderivative, what appears? A c, right? A constant. And so it's kind of like if we know the position, then we can really tell you a lot of information. Like if I know exactly where an object is at every point in time, I'm going to be able to tell you its speed at every point in time. I'm going to be able to tell you exactly its acceleration at every point in time. But if I start by knowing just the acceleration, it's very difficult for me to tell you the speed at every point in time, and it's even more difficult to tell you exactly where it was. But it turns out that the amount of information we need to go from here all the way to here is pretty minimal, as we'll see in the next few examples. So let me start with this. Let's say that we have as an example that the second derivative of some function is equal to 8x cubed plus 5. And I tell you that f prime of 1 equals 8 and f of 0, f of 1, equals 0. Make sure I copy that down. A cubed plus 8, f prime. The instructions here are to find f. Okay. I've done part of my lecture with your markers. I'm going to switch back to mine.
That's fine.
I just want to compare them. So,
Okay, that's cool.
and these feel better. in my hand.
This is bigger.
Well, I'm more used to them. All right, so here we go. So I want to know f. That means I actually want to know the function, all right? The actual function. And you can see here that this is basically like acceleration. I need to come back and get velocity. I need to come back and get position, isn't it? That's really what it is. If I start with the second derivative of something, I can build myself backwards. So let's go ahead and build backwards. Let's first start by trying to find f prime. So what is f prime going to be? It's the antiderivative of that, isn't it? I like that marker more. Sorry.
That's cool.
What do y'all think? The bigger one? Okay. We were just trying to see if these would come out better on camera or not. These other ones. We'll see. All right, so what's the antiderivative? So you can do this, right? This is just power rule. All right, cover up the 8. Antiderivative of x to the third is 1/4 x to the fourth, right? 1/4 x to the fourth, and then times 8. So you should get 2x to the fourth. Plus, now we never did one of these previously. What's the antiderivative of 5? So the derivative of what gives you 5? 5x. Remember that one. That's the one that trips people up. Right? Derivative of 5x is 5. So the antiderivative of a constant is just what? That constant with an x tacked onto it. What am I missing? Plus c. All right, so that's where I am. Now, I don't exactly know that function right off the bat. I mean, like, I don't know it exactly. I know that it's this plus some number, but I don't really know the number. Except for the fact that in the problem, they give you an additional piece of information, right? They give you this. That when you look at the derivative, if you plug 1 into the derivative, you should get 8, right? So let me come back here and let me plug 1 in. So I'm given that f prime of 1 should equal 8, right? That's given to me. So let me plug 1 into this. What would you get if you plug 1 into this? 2 times 1 to the fourth plus 5 times 1 plus c. But we need that to be equal to what? 8. So that tells me what? 2 plus 5, 7 plus c equals 8. So c is what? C is 1. So you see how I can use this one piece of information to be able to recover the entire thing. So that tells me now that f prime of x equals 2x to the fourth plus 5x plus what? 1. That is my what? F prime x? F prime of x? That's the function, right? So think about this. I think this is pretty remarkable. Let's just say we had started with acceleration, right? Just for the sake of giving this meaning. If we start here with acceleration, right? If that's acceleration. We have just recovered the exact what here? That's the velocity, right? And what did we need in order to know the velocity of the object at every point in time, right? Because this is the function. What did we need? I just needed the speed or the velocity of the object at one point in time. If you just tell me exactly how fast it was going at one point, I'll be able to recover the entire, I'll be able to describe exactly where it was, or its speed at every point in time by just knowing one point. Does that kind of make sense? But now we're not done, right? We still need to go back. We need to find f. So to get back, all the way back, we've got to go antiderivative again, don't we? And repeat this process. So let's repeat it over here. So to find little f, I'm taking the antiderivative of the derivative. And using the power rule here, cover up the 2. Antiderivative of x to the fourth is what? 1/5 x to the fifth times 2. So 2/5 x to the fifth plus 5/2 x squared plus, what's the antiderivative of 1? X plus a constant, c. Now, just because of where I know we're going on next problem, I'm going to call it D. There's no problem calling it D, right? There's no issue with that? It's just a constant, right? It's just a number I don't know. But what is it that I'm given in the problem? I was given one more thing. F of 1 was 0, right? That's given to me. That means when I plug 1 into that function, I'm going to be able to recover the exact function. By plugging 1 and getting 0, I should be able to determine D. So let's plug 1 in. You get 2/5. I'm going to go a little quicker through this. Plus 5/2 plus 1 plus D equals 0. Right? Do y'all see what I've done? Plug 1 into that. I need that to turn out to be 0. Add it up. (39/10) Is that what that is? 39/10 plus D equals 0. So D is what? Negative 39/10. So our final function, right, our final f is this. Little f of x equals, where is it? 2/5 x to the 5th plus 5/2 x squared plus x minus 39/10. Okay? So again, if I want you to take anything away from this, I want you to take that if you start out with an acceleration and you want to know exactly where something was at every point in time, all you need to know is the acceleration function, and then you need to know its speed at one point in time and its position at one point in time. If you give me just that minimal amount of information, I'll be able to go all the way back and tell you where it was at every point in time. What is it what's something in the real world we know the acceleration of all the time? Gravity, right? So if I tell you right now that I dropped something, right? I dropped a rock. You know it's acceleration already, don't you? It's the acceleration of gravity. Does that mean you're going to be able to tell me where it is? No. But all I have to tell you is its speed at one point in time and its position at one point in time, and then you'll be able to tell me everywhere, exactly where it was. I don't know, that seems kind of remarkable to me. The first time I ever learned it, I was like, seems like I would need more. All right, how about this one? This will be our last example out of this section. I guess I have to do it. All right. How about f double prime of x equals x to the negative 2, and f of 1 equals 0, and f of 2 equals 0. And also x is greater than 0. Find f. What's different about this problem as opposed to the previous one?
You don't have a f prime.
Yeah, that's right. In the previous one, I gave you the f prime at one point, and then I gave you f at one point. Here, I don't. I give you f at 2 points, don't I? So I don't give you any information about the first derivative, but I give you two pieces of information about the regular function, f. So let's just try this. First things first. If I start off with f double prime of x equals x to negative 2, what's, sorry, I wrote too many primes here. What's the antiderivative of x to the negative 2? So use your power rule on this, right? N is negative 2. So we're saying 1 over negative 2 plus 1 x to the negative 2 plus 1, right? So isn't that negative x to the negative 1? Plus, I forgot my c. So f prime of x equals negative x to the negative 1 plus c. Anyone have a question on that?
In the beginning of the notes, when you were finding the antiderivative of x raised to the negative 1,
Uh-huh.
and you turn into 1 over x?
Yes.
Not,
Good question. The reason why I didn't turn this one into 1 over x squared is because I have the power rule for this will work when, as long as n isn't negative 1, right? As long as n isn't negative 1, I can use the power rule, which is what I did. If n is negative 1, that's when I looked at it as 1 over x. And that was just to try and hopefully get something in your brain to click on, oh, natural log. Remember derivative of natural log is 1 over x? That was just so you would see that like visual connection. But we're actually here now. Yeah, because look, that's a negative 1, right? Cover it up. What's the derivative of x to the negative 1? You can't use the formula, or you can't use the power rule. So you have to use the other rule, which means it'll be natural log, right? Yes? Okay, so here's what we have. Oh, also, can I get c? I should back up here. Can I get c? I don't know what c is. See, because I don't know anything about the derivative, do I? So if you don't know, you just have to go and take the antiderivative from here. Let me do it. So what would this turn into? Antiderivative of x to negative 1 with natural log, right? Little f. So, thank you. This is negative, right? Cover it up. That's natural log of x. So I have negative natural log of, I'll put absolute value of x, that's fine. It doesn't matter, we don't have to put the absolute value. Why? Because of this that was given in the problem. But technically speaking, that's the general antiderivative of 1 over x. And then I have, this is the critical point here. What do I have now? What's the antiderivative of c? Cx. Cx. So plus cx. Because if that was a 2, you would say 2x, right? If that was a pi, you'd say pi x. If it's a c, you say cx. But then there's one more thing. Plus another constant, because I've found the antiderivative, right? And I can't use c because I already used c. So why don't we use d? See, that's why I used d last time. So these two are the antiderivatives of these two pieces, but you always have a constant at the end of any antiderivative. That make sense? Any questions? All right, now let's use this information. When I plug in 1, I should get 0. So let's plug 1 into this and see what we get. Negative natural log of 1 plus c times 1 plus d needs to be equal to 0. So what is natural log of 1? 0. The natural log of 1 is 0. So this vanishes, it's gone. And then I have what? C plus d is 0, right? That's all I have? I can't figure out what that is. All I can tell you is c plus d is 0. So I'll just write that down, I'll box it. Now let me use the other piece of information that was given to me, which was f of 2 is 0, right? F of 2 is 0? So if f of 2 is 0, that means that when I plug 2 in, I should get 0. So I have negative natural log of 2 plus c times 2 plus d equals 0. Isn't this 2c plus d equals natural log 2? What did I do there? I just moved the negative natural log 2 to the other side, and then 2 times c is 2c, and then d. So what do I have now? I have 2 equations and 2 variables. And anytime you have 2 linear equations and 2 variables, you should be able to solve for C and D by either one of two methods, substitution or elimination. So I'll do a quick substitution problem. All right, I'm going to do it with substitution. What I'm going to do is I'm going to take this one right here. I'm going to solve it for C. So I'm going to take that, C equals negative D. Agreed? Let's move the D to the other side. That means I can take the second equation and substitute in for C negative D. So I'm going to write my second equation replacing C with negative D. 2 times negative D plus D equals natural log 2. Y'all follow me here, what I'm doing?
Yes.
And this gives me what? How many D's here? This is negative 2D plus D is negative D. So negative D equals natural log 2. And that means D is natural log 2. Right? Negative natural log 2. Oh, what's going on with me today? If I know D, though, right? Natural log of 2 is a number. If I know D, then don't I know what C is? C is negative D. So change the sign of this. C is what then? Natural log 2. So now I'm ready to write out my final. So here's C and D. That's what I was trying to find. I'm ready to write out what F is. F of X was negative natural log X plus, what was it, 2C? It was 2C? Was it 2C? Yeah. CX. So what's C? Natural log 2. So you can write it, I would write it this way, X natural log 2, or you can put the natural log 2 in front of the X. Just be careful. If you write natural log 2 in front of the X, you need to make sure that I understand that this is not natural log of 2X. It's natural log of 2 what? Times X. So that's why I put the X in front, so that you would say, oh, natural log of 2 is a number times X. Do you see the difference? You have to be careful with that. And then plus at the end D, so minus natural log 2. There you go.
If you're taking the antiderivative, how come the F is like not capitalized?
Well, because we said that if you start with the little f and you take the anti, we call it big F. That was just in the definition. What we are doing is we started with a little f double prime, took the antiderivative once, got f prime, took the antiderivative one more time, and got back to f. So, does that kind of make sense? This was just to get us started with the definition. All right. That's it for 4.7. I did email an announcement out. I forgot when I did it. It was earlier this weekend. Oh, by the way, I don't know if anyone came in on Friday. I had to take my wife to the ER on Friday, so I wasn't here. It wasn't expected. So if you came by, sorry for office hours. Everything should be back to normal this week. So 4.7, I did email out the assignment. Okay, I mean not email it. Put it on the announcements. How many of you saw it on the announcements? Okay, so do those problems from 4.7, and then there's an assignment from 5.1, but I'm going to start that now. Y'all doing all right? I was not looking forward to doing that section 4.7. I don't really like that section. It's tedious, and plus by looking at you, I can tell that a lot of you already had seen that before.